What's up everyone? Today we're going to go over Leetcode 742 network delay time. So this is going to be the outline of the video. The prerequisites are Dijkstra's algorithm and knowing what a priority queue is. So first we're going to go over what the question is asking, then I'll look at some of the diagrams, and then we'll look at the code and the complexities. Okay, let's look at the input and the output. The input is two integers and a 2D array of int. Now this represents the edges in our DAG. The output is also going to be an integer, which represents the total amount of time it takes to go from the origin node k is equal to 1 to all the nodes we can possibly visit. Now of course we want this in the shortest amount of time, so we're going to take the shortest path every time we visit a node. So this problem essentially boils down to Dijkstra's algorithm. Think of it as water flowing out from the origin node. So if we're starting at k is equal to 1, after 1 second, we can visit node 0. After 2 seconds, we can visit node 2. And then after that, well, we can actually get to 3 from either 0 or 2. But because we want the shortest path, we are going to visit from node 2. So the total amount of time it takes to visit all the nodes from k is equal to 1 is 5. Now I'd like to point out a distinction between BFS and Dijkstra. And we see that it's just a matter of one extra dimension, and the problem essentially becomes a standard BFS. Now, I'd like to point out the difference between BFS and Dijkstra's. For the purposes of this problem, our Dijkstra's is nothing but BFS with an added dimension of distance. What do I mean by that? Let's take a look. So here's our DAG, and a standard adjacency list representation of it would look like this. 0 to 3, 1 goes to 0 and 2, 2 goes to 3. So let's ignore the distances for now. In a standard BFS, we also have a visited set, which ensures that we don't visit the same nodes again. So 1, 0, 2, and 3 is just how we might visit this DAG. And in a BFS, we have a queue, and the data type is integer, and we pull in the order that we add, so it's FIFO. Now for Dijkstra's, there's one added dimension of distance. So 0 also keeps track of 3, but we add a dimension of distance. So 0 to 3, it has a distance of 6. 1 to 0 has a distance of 1. 1 to 2 has a distance of 2. 2 to 3 has a distance of 3. So to represent this, we're going to use an integer array. Pretty much, this is the same thing as before, standard BFS, but since we're adding one dimension, we're not going to just have an integer, but an integer array, where it's going to look like this, and the first entry is going to be the node number, and the second entry is going to be the distance. Now let's look at the set. So we usually use a set of integers for the visited, but since we're adding an extra dimension, we're going to convert the set into a hash map. Now for the last one. We usually use a standard queue in our BFS. When we're doing Dijkstra's, we use a priority queue. Why do we do that? Well, in a regular queue, we are going to pull in the order that we input. But for a priority queue, we are going to pull not in the order of the input, but we are going to pull according to the shortest distance. It's easy to see this because we are adding one dimension to all the integers that we usually use. So we simply use an integer array for this. Now we're going to have to use a custom comparator and make sure that since we want the shortest distance, the one that gets pulled acts like a min heap. Now let's do a diagram dry run. Now let's do a dry run of this problem. So we have the same graph and k is equal to 1, which means we start from the first node. So in the beginning, we are going to initialize our distance map and our priority queue with our origin. Since we're starting from the origin, the distance is going to be 0. So first, what we do is we poll the node in the priority queue, the first node in the priority queue. And then we check its neighbors. So 1 can go to 0 or 2. Before doing anything, 1 is going to check if its neighbors are part of the visited distance map. They are not, so it's going to add both the nodes. 0 and 2. What about this extra dimension of distance? Well, to go from 1 to 0, it takes distance 1, and to go from 1 to 2, it takes distance 2. Now keep in mind, priority queues automatically order themselves. Are the distances in ascending order? They are, so we're good. So for now, 1 has created 0 and 2 in the queue. It's polled itself, so we're done. Next iteration, we are going to poll the node which has the minimum distance. In this case, it's 0. 0 has a neighbor of 3. Now 0 is going to first poll itself, and if it's not, since it's not in the visited distance map, it's going to add itself. And it's going to check its neighbors. Well, its neighbor 3 is not part of the visited distance map, so it's going to add it to the queue. What is the distance to get to 3 from 0? Well, from 0 to 3, it takes 6, plus the distance to get to 0 is 1. So the distance is going to be 7. Now, 0 is done. Now next, it's going to be the turn of node 2, because the priority queue automatically orders according to distance, the shortest distance. So 2 is going to check its neighbor. 2 has a neighbor of 3. 2 is going to add 3 because 3 is not part of the visited distance map. So after 2 is going to add 3, it's going to set a distance of 5 because this is 3 and the distance to get to 2 is 5. Now at this point, 2 is already part of the distance map. Keep in mind the priority queue always shuffles itself. So you see that these two are out of order. This is going to get swapped for 3, 5 and 3, 7. So node number 3, which came as a result of node number 2 with a distance of 5, is going to be at the start of the queue. Next iteration, 3 is going to poll itself, and after it checks that it is not part of the visited distance map, it is going to put itself here, and it's polled, and then it's going to see if it has any neighbors. It does not, so it finishes. Next, we still have a node in the queue. So 3 is going to poll itself. It sees that it has no neighbors, and it sees that it's actually part of the visited distance map. So it does not do anything, and we're done. Next, I'm going to show you an algorithm visualization so you can see the whole thing in a smooth manner. Pay attention to how the priority queues are changing and see how the nodes are getting highlighted. Okay, so first we're going to take our adjacency list representation and we're going to take our priority queue. We make our priority queue a min heap according to the distance or the second integer in our integer array. Then we go through the edges that we're given and we initialize our adjacency list. Then we make our distance map, which stores the node as the key and the value as the distance it took to get to that node. Then we initialize our priority queue. And I made an integer called max, which is what we're going to return for this function. So first, we put our origin into the distance map and initialize it to a distance of 0. Next, we're ready to start polling our queue. What we're going to do every iteration is poll the integer array and call it cur, and we're going to take the node and the distance. And every iteration of the priority queue getting polled, I'm going to check if we have reached a max distance, which is larger. So max is going to be math.max of the integer max and every distance that we get from polling the queue. If the distance map contains the node, we can't do the rest of this. Otherwise, we add the node and the corresponding distance to our distance map. Next, we're going to see if our adjacency list map contains the node we've polled. And if it does, we're going to check its neighbors. So each one of its neighbors is going to have a node and a corresponding distance. So every time we iterate through the neighbors, we're going to see if the neighbor node exists in the distance map. If it does not, then we add that to the queue. And we add it according to the node as the neighbor, and the value is going to be the distance from here and the neighbor distance from here. Once we're done with our priority queue, what we're going to return is this check. We see if we were able to visit every single node. How do we do that? Well, we have a visited distance map and we check its size to see if it's equal to n. If it is, we can return the max. Otherwise, we have to return -1. We return -1 if there was a node we were not able to visit. Now let's look at the time and space complexities. The space complexity is going to be big O of n plus e. N because we might potentially visit every single node in our distance map, and e because we're adding all our edges here. Now the time complexity is going to be ElogE in this implementation, because adding to a priority queue or min heap is going to be of n log n. And since we might do it e times in the worst case time scenario, the time complexity is going to be big O of E log E. Alright guys, so that's how you solve Leetcode 742. If you liked the video or disliked the video, thumbs up or thumbs down. And if you'd like to see more, don't forget to subscribe.